All right, think about your digital life for just a second. Every single email you send, every cloud transaction you authorize, every prompt you feed into an AI or video you stream. To us, sitting at our screens, it feels completely instant and, well, weightless, right? But there is a massive, hidden energy footprint to all of it. We usually only see the pristine results on our devices, but behind the scenes, millions of computers are just devouring vast amounts of electricity, and as a direct physical result, bleeding out massive amounts of waste heat. So in this explainer, we're going to explore a truly mind-bending question pulled straight from the latest research on sustainable IT. And that question is, can we fundamentally redesign computing systems so they waste a fraction of the energy simply by changing the very physics of how they compute? So here's our roadmap for this explainer. We'll cover the hidden energy cost, reaching the physical limits, reversible computing, adiabatic computing, the ultimate combination of the two, and finally, what this means for a sustainable digital future. Section 1. The hidden energy cost, the invisible footprint of digital growth.
You know, it's really time we rethink our mental definition of digital infrastructure. We always picture these quiet, cool, pristine data centers, but the physical reality? It's intense electrical processes. Every single computer, from the smartphone in your pocket to those absolute behemoth server banks running global AI models, they all consume electricity and they all release waste heat. And as our reliance on digital services just completely multiplies, this heat problem is multiplying right alongside it. It's demanding these incredibly energy-hungry cooling systems literally just to keep the machines from melting down.
Section 2. Reaching the physical limits. Why we can't just shrink chips forever.
For decades, our go-to solution for hardware problems was simply to make things smaller. This trend was actually measured in part by something called Kumi's law, which basically observed that the number of computations we could pull off for every unit of energy, every joule, historically improved at this incredibly rapid, predictable pace. Doing more useful work with less electricity, well, that allowed us to lower emissions while growing our tech. But here is the massive warning sign. This trend is slowing down. We're actively seeing the end of Dennard scaling and a real deceleration in Moore's law. Basically, our traditional approaches are hitting a physical wall.
Just look at this historical progression. We went from these massive, clunky vacuum tubes in the 1940s to consumer laptops in the 90s, to global cloud servers, and now to these incredibly dense AI chips. We've squeezed immense efficiency out of this traditional model over the last 80 years. But trying to wring out the next drop of efficiency, doing even more useful work with even less electricity, is becoming exponentially harder with the way we currently build hardware. So, to understand exactly why we're hitting that wall, we actually have to look at the physics, specifically Landauer's principle. This principle states that when a computer erases information, a minimum amount of energy absolutely must be dissipated as heat. Information processing just isn't fundamentally free. In conventional computing, overwriting or erasing a single bit has this tiny energy cost. But when you take that minuscule loss and multiply it by billions or trillions of operations happening every single fraction of a second, you get massive amounts of heat.
Which leads us to a pretty profound pivot. If we can't just rely on building slightly greener data centers or writing better software optimization forever, we have to ask the big one. Can we design computing systems that waste far less energy by fundamentally changing the very physics of computation itself?
Section 3. Reversible computing saves information, redefining how we process data.
Right now, conventional computing is mostly irreversible. Once it spits out an output, the original input is gone permanently. And as we just learned from Landauer's principle, that data loss directly equals heat. Well, reversible computing completely flips the script. It uses operations that can be undone exactly, meaning you could theoretically reconstruct the original input directly from the output. The legendary physicist Richard Feynman was actually deeply interested in this. He concluded that if a computation is truly reversible and no information is permanently lost, there is actually no theoretical minimum energy required for the computation itself. I know it sounds like actual magic, but it's pure physics.
Now, obviously, you can't just flip a switch on your laptop to get there. There are some major real-world engineering hurdles. For starters, we would need entirely new circuits and entirely new logic gates. Even our software is fundamentally incompatible right now. Traditional programming constructs, like your standard coding loops, they're irreversible by their very nature. But researchers are aggressively going after this, developing new energy-efficient languages. A prime example is MIT's EEL language, which is being designed from the ground up to eliminate irreversible code and stop that energy bleed. Section 4. Adiabatic computing reduces heat, changing how circuits switch.
Okay, a quick physics lesson. An adiabatic process basically means no heat is exchanged with the environment. So let's look at how that applies to our computer hardware. Traditional digital circuits switch incredibly fast. Think of it like aggressively snapping a hard light switch on and off. That abrupt change in voltage wastes energy as heat. Adiabatic computing, on the other hand, is much more like using a smooth dimmer switch. It uses carefully controlled super-gradual voltage and current changes to transition from one state to another. And that smooth transition is exactly what prevents that precious energy from escaping as waste heat.
But here's the catch, the trade-off we have to talk about. It's raw speed versus ultimate efficiency. Because adiabatic computing completely relies on those gradual controlled transitions, it often has to operate more slowly than our traditional snap-switching circuits. So it's a classic engineering balance. This tech won't necessarily replace the ultra-high-speed processor in your gaming rig tomorrow, for sure. But for massive, heavy-lifting workloads where raw, blistering speed can take a backseat to ultimate sustainability, it offers incredible promise.
Section 5. The ultimate combination. Merging adiabatic and reversible processes.
So what happens when we mash these two concepts together? It builds into an entirely new paradigm, adiabatic reversible computing. Step 1, we use reversible logic to ensure we never permanently lose information. Step 2, we use adiabatic processes to smoothly control the voltage transitions so we don't leak out heat. And step 3 is where the magic really happens. Because the entire system is both reversible and perfectly controlled, the energy used in one operation can actually be looped straight back into the system and reused for the very next step, rather than just bleeding out into the environment as wasted heat. It's brilliant.
We do have to ground this in reality for a second, though. Commercial-grade microprocessors using this ultimate combination, they are not widely available just yet. This is still very much in development. The need for highly specialized hardware, increased programming complexity, and of course those slower operation speeds, they all remain pretty significant hurdles. But listen, as AI and cloud workloads absolutely explode around the globe, finding a way to reduce waste heat at the foundational circuit level is quickly becoming a vital, strategic priority for the entire tech industry. Section 6. A sustainable digital future. Expanding efficiency to the real world.
Now, the concepts we've been discussing actually bridge directly into some wildly advanced fields like adiabatic quantum computing. This is a highly specialized form of quantum computing that uses these exact same adiabatic processes, but specifically to solve complex optimization problems. Rather than running standard code, the system begins in an initial state and smoothly, gradually evolves toward a final state that represents the absolute most optimal solution to a problem. In fact, companies like D-Wave are already out there building quantum annealing systems based on these very principles.
And here is exactly why this matters so much outside the walls of the data center. When we use adiabatic quantum computing for optimization, we can apply it to massive, real-world systems. I mean, we're talking about dynamically routing entire cities' traffic to eliminate congestion and emissions. We're talking about streamlining global logistics, managing incredibly volatile power grids, and greening entire international supply chains. By rethinking computing down at the physics level, we don't just lower the IT footprint, we're creating tools powerful enough to help decarbonize entirely different industries.
Which brings us to a huge, foundational takeaway from our source material today. The future of sustainable IT will depend not only on cleaner energy, greener data centers, and better software, but also on rethinking computation itself. We literally cannot just keep trying to cool hotter and hotter chips. True sustainability is going to require us to innovate at the deepest, most foundational, physical levels of our technology. So, if you're an IT professional, a student, or honestly just someone who is deeply curious about leading this green transition, the concepts we've explored today are drawn straight from Chapter 13 of this really incredible book, Making IT Sustainable: Techniques and Applications by Mikhail Glukovtsev. It's just an essential guide to the frameworks and real-world applications for making our digital infrastructure truly green. And it leaves us with this massive, thought-provoking question to ponder. Will the next great leap in human computing come not from making our chips smaller and faster, but from fundamentally redesigning them to be reversible? Thanks for joining me on this explainer, and I'll catch you next time.